We're going to finish up regulating blood pressure and blood flow to the organs. So we talked about in the last lecture about controlling blood flow to the organs and how that's auto-regulation, so local factors are going to affect whether you vasoconstrict or vasodilate to the organ. And now we're going to take a look at how we regulate blood pressure. And that's under the control of the nervous system and endocrine system, which makes sense because remember, nervous and endocrine systems are in charge of controlling homeostasis. So nervous system is going to provide short-term control of blood pressure, and the hormones will provide long-term control of blood pressure. So with short-term regulation, this is seconds to minutes of the blood pressure getting out of the normal range. Nervous system will jump in, and it's going to regulate the cardiac output by affecting heart rate and stroke volume, and then also it's going to affect blood pressure by affecting the total peripheral resistance. So an example that we're going to talk about is the baroreceptor reflex, and that's going to involve the heart and the blood vessels. And if short-term regulation by the nervous system doesn't fix the problem with the blood pressure, then the endocrine system will come and take over. So minutes to days will be our long-term regulation with the hormones. And the hormones are going to talk to the kidneys, and they're going to regulate how much urine is produced, and that'll regulate the blood volume, and that'll affect the blood pressure. So this is just a nice summary of regulating blood pressure. So who's in charge short term? We have nervous system, and it's going to change the blood pressure through the cardiovascular system. So looking at our baroreceptor reflex, we're going to be affecting the heart rate, stroke volume, and the total peripheral resistance. And then long-term control of blood pressure will be the endocrine system, and that's going to work through talking to the kidneys and affecting the blood volume, so how much urine is produced or not produced, and that'll affect the blood volume. So let's take a look at how the nervous system controls blood pressure in the short term. So there's a cardiovascular control center that's in the medulla oblongata of the brainstem. And this is the integrating center. It's going to get all the information coming in about what the blood pressure is, and then decide if blood pressure needs to be changed or not. So the cardiovascular control center is going to receive input from a number of places. You don't need to memorize this list, but there are some baroreceptors. These are sensory neurons that detect pressure, because baro means pressure. So there's some arterial baroreceptors, and we also have some baroreceptors in the vena cava and right atrium, and they're going to look at the venous pressure. We do have some chemoreceptors telling the cardiovascular control center information about carbon dioxide, pH, oxygen, and then we have proprioceptors because when you start exercising, you're going to need to increase your blood pressure a little bit. And then also higher brain centers like your cerebral cortex and hypothalamus can also affect blood pressure. So we especially see that like when you're angry at somebody, your blood pressure will rise. And then the cardiovascular control center will look at all the information coming in and decide if it needs to change the blood pressure or not. And if it does decide to change the blood pressure, it's going to send motor signals out through these sympathetic neurons and parasympathetic neurons. So remember that the sympathetic nervous system is going to innervate the SA node, the ventricle walls, and then the smooth muscle in the arteries and in the veins. So it's going to innervate the SA node, ventricle walls, arteries, and veins. The parasympathetic nervous system is only going to innervate the SA node, so it's only going to affect the heart rate. So let's take a look at the baroreceptor reflex. This is a really important negative feedback loop to help keep the blood pressure in the normal range. So in our negative feedback loop, the sensors going to be checking what the map is, would be the baroreceptors. And then our integrating center is our cardiovascular control center in the medulla oblongata in the brainstem. And then it will decide whether to change the blood pressure or not, and if it does, it'll send motor signals out through the sympathetic and parasympathetic neurons. And the targets, the effectors that are going to work to change the blood pressure will be the heart and the blood vessels. So the baroreceptors that are checking what the mean arterial pressure is are going to be located in the aorta and also in the carotid arteries. So the reason that the body chose to put baroreceptors here is that we want to make sure that the blood pressure is high enough in the aorta so that we can get blood around to the rest of the body. And then we also have baroreceptors in the carotid arteries because you want to make sure there's enough blood pressure to get enough blood up to the brain. So the baroreceptors are going to be using frequency coding to let the brain know what the blood pressure is. So depending on the blood pressure, they're going to send a different number of action potentials to the brain. So you can see when the blood pressure gets too high, they really increase their frequency of action potentials, and then when the blood pressure gets too low, they decrease their frequency. So here's our cardiovascular control center that's in the medulla oblongata of the brain stem. And if it decides that it needs to change the blood pressure, it can send signals out through the parasympathetic neurons to affect the SA node. And then the sympathetic neurons, remember, they're going to innervate more places. So they're going to innervate the SA node, affecting heart rate. They're also going to innervate the ventricle walls. That'll affect the stroke volume. And then they also innervate the walls of the arterioles and the veins. Here's a nice summary of the output of the cardiovascular control center from the brainstem. So it's going to use sympathetic neurons innervating the SA node, and if you increase sympathetic stimulation of the SA node, that will increase the heart rate. And if you increase the heart rate, that'll increase the blood pressure. Sympathetic stimulation to the ventricle walls, it will make the ventricles contract harder. That'll increase the stroke volume, the amount of blood that's squeezed out in one contraction or one beat. And if you increase stroke volume, that will increase the blood pressure. Sympathetic neurons also innervate the smooth muscle of the arteries. So when you increase sympathetic stimulation, you'll constrict the arteries, so will cause vasoconstriction. That'll increase the resistance, which will also increase the blood pressure. And then sympathetic neurons also innervate the smooth muscle of the veins, and so that'll cause the veins to vasoconstrict. That'll increase venous return to the heart. You'll fill the ventricles up with more blood. That increases the end diastolic volume. We'll stretch the ventricle walls closer to the optimum sarcomere length. They'll contract harder, and so they'll squeeze more blood out with each contraction, so that'll increase the stroke volume. And if you increase the stroke volume, that'll increase the blood pressure. The parasympathetic nervous system only innervates the SA node. And so if you increase parasympathetic stimulation, that will decrease the heart rate. And if you decrease the heart rate, that'll decrease the blood pressure. So let's take a look at the baroreceptor reflex when the blood pressure is too high. So we have hypertension. So the baroreceptors in the aorta and carotid arteries will send that information to the cardiovascular control center in the medulla oblongata. And then medulla oblongata says, well, we've got to decrease the blood pressure. So it's going to do that by increasing parasympathetic activity and decreasing sympathetic activity. So if you increase parasympathetic activity, remember the parasympathetic neurons only innervate the SA node. So that'll decrease the heart rate, and if you decrease the heart rate, that decreases blood pressure. And then if we decrease sympathetic activity, so it innervates the SA node, that'll decrease heart rate, that'll decrease the blood pressure. And then sympathetic neurons also innervate the ventricle walls, so now the ventricles will not contract as hard. That will decrease the stroke volume, and if you decrease the stroke volume, that decreases blood pressure. Decreasing sympathetic activity to the arterioles will cause them to vasodilate, so that will decrease their resistance, and if you decrease the resistance, you'll decrease the blood pressure. We're also going to vasodilate the veins, and that'll decrease the venous return to the heart, which will decrease the end diastolic volume, which decreases stroke volume, and a decrease in stroke volume decreases the mean arterial pressure. And then if we had the opposite problem, if we had hypotension, blood pressure is too low, the baroreceptor reflex is going to kick in and work to increase the blood pressure. So we're going to do the opposite, and we're going to decrease parasympathetic activity and increase sympathetic activity. So if you decrease parasympathetic activity of the heart, that will increase the heart rate, and increasing the heart rate will increase the blood pressure. And if you're increasing sympathetic activity, that will increase heart rate as well and increase blood pressure. We're also going to make the ventricle walls contract harder, which will increase the stroke volume, and increasing stroke volume will increase the blood pressure. And then if we increase sympathetic activity to the smooth muscle in the arterioles, that will cause them to vasoconstrict, which will increase the resistance. And if you increase the resistance, that'll increase the blood pressure. And then we're also going to vasoconstrict the veins. So that'll increase the venous return to the heart, which will increase the end diastolic volume, which makes the ventricle contract harder, and that will increase the stroke volume. And increasing the stroke volume will increase the blood pressure. We do have some hormones that are also involved in regulating the blood pressure short term. So epinephrine, remember that's going to be stimulated to be released with sympathetic stimulation of the adrenal medulla. We're going to talk about ADH and angiotensin II a little bit later when we get to the kidneys, but all of those hormones are going to cause vasoconstriction, and that'll increase the resistance and increase the blood pressure. And then the other things that epinephrine will do, it also will increase heart rate and increasing stroke volume as well. And all of those will increase the blood pressure. So the baroreceptor reflex, it does respond very quickly to short-term changes in blood pressure, but it does adapt to prolonged high or low blood pressure, and then it no longer responds. So the endocrine system will take over with hormones. The hormones are going to talk to the kidneys, and they will regulate the blood volume, which will affect the blood pressure. So for example, if the blood pressure got too low and the person is hypotensive, then we want to increase the blood volume, and that will increase the blood pressure. So how the endocrine system does that is it will stimulate the secretion of ADH. That's coming from the posterior pituitary. And remember, ADH is antidiuretic hormone, so that will tell the kidneys to save water from the urine and put it back in the blood. And if you increase the blood volume, that will increase the blood pressure. And then there's also aldosterone, which we're going to talk more about when we get to the kidneys. But aldosterone is also going to tell the kidneys to save water as well. And so both ADH and aldosterone tells the kidneys save water, and that'll increase the blood volume, which will increase the blood pressure. If the blood pressure is too high, then the endocrine system will work to decrease the blood volume and tell the kidneys don't save as much water, so urinate more, and that'll decrease the blood volume and decrease the blood pressure. So if the blood pressure is too high, then we're not going to release as much ADH or aldosterone. And this is just a nice summary of controlling blood pressure. So if the blood pressure is too low, short-term fix, we're going to stimulate the sympathetic nervous system with our baroreceptor reflex, and that'll increase the heart rate and stroke volume and also cause vasoconstriction. All of those will increase the blood pressure. Long-term control of the blood pressure, if the short-term fix with the nervous system doesn't work, the endocrine system will step in, and we're going to be releasing ADH and aldosterone, and both of those will tell the kidneys to save water, and that'll increase the blood volume and increase the blood pressure. And then this table is just showing you the summary of the nervous system and endocrine factors that affect blood pressure. There is a mistake. Under the SA node with the parasympathetic nerves, it says that parasympathetic increases the heart rate. That's not right. It actually will decrease the heart rate. So just make that correction in your notes. The other thing I want to point out in this table is that if you look at all of these things that are working to change the blood pressure, Most of these things are dealing with increasing the blood pressure. So your body has a lot more controls to increase the blood pressure than it does to lower it. And that's because hypotension can kill you very quickly, whereas it will probably take several years to kill you with high blood pressure. Thermoregulation also affects blood pressure. So when you're exercising, your body temperature will rise, and we need to get rid of that extra body heat. So we're going to vasodilate the blood vessels in the skin to dump off the extra body heat. So if we do that, if we vasodilate to the skin, that's going to decrease the resistance, and that could possibly decrease the blood pressure. So the body had to kind of decide, which is more important, your body temperature or keeping your blood pressure up. And it decided that it's more important to make sure that your body temperature stays in the normal range than blood pressure does. Let's take a look at all of the things that are affected when you exercise. And here's a nice graph that shows everything. So when you start exercising, your heart rate will increase. Your stroke volume is also going to increase because of sympathetic stimulation to the ventricle wall. And also we're increasing the venous return to the heart by either sympathetic stimulation with vasoconstriction of the veins, we've got a respiratory pump, and we've also got our skeletal muscle pump going on. So heart rate and stroke volume, if both of those are increasing, we're going to increase our cardiac output. So remember, that's the blood flow. And we really want to increase the blood flow to the skeletal muscle and also the cardiac muscle. So we actually end up vasodilating to the cardiac muscle and the skeletal muscle. So overall, we experience a drop in our resistance. So if we take a look at our mean arterial pressure, even though the cardiac output goes way up, but because the resistance goes down, because we are vasodilating to the skeletal muscle and the heart and possibly to the skin if we're hot, all of that will keep the blood pressure from rising too high while you're exercising. So the mean arterial pressure will go up a little bit during exercise, but it's not going to go through the roof because you are vasodilating to the skeletal muscle and the cardiac muscle.